I'm not recording them. Okay, so what I'm going to do is, excuse me, I have an ongoing cough, by the way, so occasionally, that's why I'm sucking on a lozenge. Okay, I'm going to go ahead and get into this big time right away. Okay, so what I'm going to do is continue on from last week. Now, last week we talked about, we spent most of the time talking about significant figures. Now, I want you to remember that significant figures are going to apply for the rest of the semester. Whenever we're doing math, excuse me, in lecture and in lab, goodness, always have to consider significant figures. Okay, and I spent quite a bit of time last time talking about significant figures. Now, if you weren't in the class, then I record all videos. So that video is recorded. If you go to modules, you'll see the recording. Okay, it also introduces the class in terms of the syllabus, how I grade, etc. Okay, then I gave an example of a problem, a typical dimension analysis problem. I said, let's convert 30 days into seconds. And then we went through a process. Okay, so I'm going to reiterate this process here. Okay, so this is the process you'll be going through. Let me get us some room here. Okay, so these are the 4 steps on all the dimension analysis, the mole conversions, and the stoichiometry problems in this class. There are 4 main steps. Now, step number 1 is says, if there's a reaction, balance it. If there's a chemical reaction going on. If there's no chemical reaction, you just skip it. Step number 2 is what's given. What are you trying to calculate? Okay. So when we talk about what's given, you're going to be putting that on the left side. What's to be calculated, you're putting on the right. And then we're going to go through conversion factors to go from the left to the right. Okay, so let's look at an example of a dimensional analysis problem. So how many, let's do a time problem again here. How many seconds are in let's say a year. Okay. All right. And this is a non-leap year. Okay. So all problems, again, we have the 4 steps. Step number 1, is there a chemical reaction going on? No. So we skip that. Step number 2 is what's given. What's given? Okay. Well, what's given is 1 year. So that is going to go on the left. And when we try to calculate seconds, that goes on the right. Now, to go from the 1 year to seconds, we're going to be going via conversion factors. Okay, that's number 4 here. Okay, and conversion factors are fractions. And those fractions are going to have to go through, and we have to cancel the units. In other words, the years have got to cancel, and when we're all done, we have to end up with seconds. Okay, so is there a conversion factor to go from years to seconds directly? No, so we're going to have some intermediate steps to get there. It could be excuse me, could be 2 steps, it could be 3 steps, it could be 10 steps. The point is there are intermediate steps. And almost all the time, those steps are fractions with units in there. Okay, so step 1 is, what do we know about years? Well, we know there's 12 months to a year. So let's do that. Now the question is, we have 12 months, 1 year. That's one fraction. Or we have 1 year and 12 months. That's the other conversion factor. So you always have a fraction. So the idea, though, is we want the year to cancel. That means the year has to be on the bottom. Okay, so now we're in months. Now, do we have a conversion factor to go from months to seconds? No. So now we need to go to, now here we can go one of 2 ways. We can talk about weeks in a month or days in a month. Okay, let's do, I don't know, let's do, since this is a non-leap year, let's just say there are 4 weeks per month. And again, notice the months have to cancel. So now we have weeks. If we multiply all those numbers out, we'll have weeks in a year. Now we need to know, and again, we're eventually going towards seconds. So the next one is how many days in a week? Now, hours in a day. Yeah, was there a question? Cindy, mute your computer. Okay, so we need to convert. We have to have something with days in it, so it cancels. And we're going to talk about hours in a day. And again, these are conversion fractions or conversion factors. They're always fractions. And you can see this kind of goes on and on. And we want to end up with seconds. And this is a very, very generic type problem where we're going to run a series of conversions, starting with what we're given all the way to what we're supposed to calculate. And then how many, we have 60 minutes in an hour. And then finally, we have $60 seconds to a minute. I want you to notice with the setup here, all the units cancel except for what we're trying to calculate. If that's not the case, your setup is wrong, okay? So this is the concept of dimensional analysis. We're analyzing the dimensions, and we're going to throw in conversion fractions or factors that convert our given over to what we're trying to calculate. Now, if you're in my lecture for this class, and this was a problem on a test, this is worth 90% of the credit. The answer is worth 10%. The answer means you know about significant figures, and you also know about how to use your calculator. The chemistry part is the setup. That's why I give you more credit for the setup than the actual answer. Now 90% is an A in this class. So that means you could go through this whole set of problems without using a calculator and getting 90% for each one of them and still get an A on the test, assuming there was a bunch of conversion problems. Okay, so to do this problem, in our calculator, we're just going to multiply everything on the top, divide everything on the bottom. Okay, so are there any questions so far as to this setup? This is like an official by the textbook setup. Okay, grinding that on my calculator, assuming I put all the numbers in right, we end up with now sig fig wise. This is an interesting problem. What do you think the sig figs are for this problem? How will we analyze this? Now, this is a tricky problem for sig figs.
Okay, so what immediately came to mind was, I know with sig figs, it cannot be more accurate than the units that were used to measure it, right? Or like the smallest. And in this case, I see like one significant figure being the smallest, but I think that doesn't make sense. I would think it'd be two significant figures.
Okay, that's interesting.
And what I see with one significant figure is like 1 year, 1 month, 1 week. Isn't that one significant figure?
Yes and no. Remember with significant figures, if we have a definition, that doesn't count. In other words, how many seconds are in a minute? Exactly 60 into 1 minute. So does this mean it's one sig fig? No, because it's by definition.
Okay.
All right. So those, when we have infinite significant figures, we don't worry about them because they're always going to be bigger than anything else. So the only thing here in this problem that's not a definition is our given 1 year. How many sig figs is that?
Is that 0 sig figs?
One.
Okay.
Okay, that means our answer. So all these others are definitions. Every single one. That means every single one of these has infinite precision because it's by definition. The only one that doesn't have a definition is the given 1 year. Now I could have stated it 1.0000 years, or I could have just said 1 year. Because I said 1 year, that automatically makes the answer one sig fig. Okay, so here we have, by my calculator, 29,030,40, all these numbers. Good old calculator gives you, underneath the covers of calculator, anywhere from 12 to 29 sig figs, depending on your calculator. And we never work with that many sig figs. That means we always have to look at our answer in terms of what our answer should be in terms of significant figures. Okay, so how do we convert this guy here to one sig fig? You guys have any ideas?
Scientific notation.
Exactly. That's the way I would approach it as well. Okay. One way to do it is scientific notation. The other way is just to look at the number itself. Okay, let's look at the number itself first. Then I'll show you how cleanly using scientific notation works better. Okay, so we've got Now, whenever you convert a number to a certain number of sig figs, you go to +1. So that means we're going to the second significant place, okay, which is the 9 year. The 9 is 5 or more, so we're going to increase this by 1. That makes that a 3. But we have to put zeros in as placeholders. So that means this is going to be 3, 0, 0, 0. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, so that's the answer. One significant figure. Or that. Between the two, that is preferred.
I have a question.
Yes.
In this case, it doesn't seem like that's very close to our original answer. Like, so is that just like not a very accurate answer, or what? How would you describe that? Since it's about like almost a million numbers.
Oh yeah, I totally agree. But see, our original given isn't very accurate either. It's 1 year. Is it exactly 1 year? Well, we don't know.
Right. Okay.
And it's a very good question. Very good question. That's why I said, I could have said 1.00000, another exactly 1 year, or just a year.
Okay.
A year has got approximately, what is that, 30 million, about 30 million seconds.
Right, right.
That makes sense?
Can you explain those infinite signals one more time and that definition?
Yeah. No, when I say by definition, when I ask you how many days in a week, you immediately say what?
7.
7? Is it 7.1?
I see. No, it's not.
6.9? No, it's exactly 7.
I see. So in those cases, like they're all definitions.
Yeah. And when I say how many days in a week, is that measured by an instrument? No, you look it up on a table. It's by definition.
Okay.
And normally, there are no decimal points in a definition as well. No decimal points there. So if you see, I don't know, I don't know, seconds per for 1 Yountville. And just made a, as soon as you see the decimal point there, that means it's measured. That means that is a 4 sig fig number.
Uh-huh.
Okay. Okay.
Yes, that makes more sense because it's not.
Yeah, I know it's weird.
Definition.
Yeah, I agree. To me, it's going like 3 is the answer. Yeah. And that's because in life, when you use an instrument, you can use a very expensive, high precision instrument, or you could use some, dumbass instrument from 50 years ago that has no precision at all. Back in, I cook a lot, and I have a digital scale in my kitchen for measuring stuff. Okay, well, 50 years ago, I'm an old guy, when I used to cook, I had a spring-loaded scale in my kitchen to weigh stuff. Well, guess which one's more precise? The digital one. The spring-loaded one was just the accuracy of the spring. Excuse me. Spring gets old, it gets weaker, all this stuff, where a digital one doesn't. And so the digital one is going to be more precise than the old spring one. So you're going to have more sig figs associated with the digital one than the old spring one. But again, it's measured. Now that includes eyeballing it as well. When we get into lab, we're going to be doing wet chemistry, and you're going to be measuring things with your eyeball. But you're going to have to also, I am going to an allergist, you guys. I have a negative COVID test, all this stuff. I just moved from the state of Washington about a year ago, and I was on allergy injections up there, and my cough was totally zero. As soon as I moved down here, I must be allergic to something. Anyway, hopefully this improves. Okay, so let's just do some other, this worksheet's from Chem 300. These are some more digital analysis.
I have a question. Is this in a folder on Canvas somewhere?
Yes. If you go to modules, down on review worksheets, you'll see dimensional analysis. Here's a zip file. Okay. The zip file is all of the files under dimensional analysis. So these are all the files under dimensional analysis. So you can take one of these files, you know, problems on sig figs and all this stuff, scientific notation. If you take all those in a zip file, that's the zip file available. So if you want all of them, download the zip file. If you want them individually, you can download them individually. Does that make sense?
Yes.
And by the way, while I'm here, for the people that are new in the class, under administration, or general information in terms of modules, we've got, you're going to be signing a lab safety contract next week when we get into lab. Here's the syllabus. That's how I grade, how to contact me, etc. And here's the lecture lab schedule. Now, I want you to notice a couple things here. That's 3.000. That's revision 3.00. If I revise that, that number is going to go to 3.01 or 02 each time, okay? So that'll tell you what version you're looking at. For example, if we pop over to the syllabus here. Okay, so here's the syllabus. And it is going to have, it should have 1.00 in the top right. Because I haven't uploaded the current one. Anyway, so here is the syllabus. Okay, I included Dr. Atkins' lecture schedule in that as well, since I'm doing the lab for her lecture. Okay, and if you go to the end, here's required materials. I've downloaded this OER free textbook for you as a PDF, or you can do it online if you use that link. There are no exceptions. You got to have a goggles, and it has to be splash proof or indirect venting. Here's the lab manual, also required. And I've listed an optional lab book, and that's just a concise place to put notes and stuff like that, and that's optional. Here's how to get a hold of me. If you go to the very end, here's our grading. Now in this class, just go over this real quickly. You're in the lab portion of Chem 400, okay? 85% of your grade will come from Dr. Atkins' exams and other ways to get points in their class. 15% of it will come from my class, which is the lab portion. Okay, you're going to end up with each lab will be worth 10 raw points. So say we have 12 labs, that means you're going to end up with 120 possible raw points. I would then convert that to a percent, and then convert that then to 15% of that percent. And that's what I would then tell Dr. Atkins what you got in the class. Okay, does that make sense? So no matter how many labs we do, each one is worth 10 raw points. And then those raw points will be converted to percent, and 15% of those will go to Dr. Atkins. Okay, does that make sense? Now, next week, I'm going to go into the lab write-up, because there's an extensive lab write-up for each lab. Let's see. So here's the lab part of her lecture here. Now, this school does not give minuses and pluses, so it's either A, B, C, D, or F. So basically, it's 89.5 to 100 is an A, 79.5. Okay. Now, that's if you had me for lecture and lab. I round. I don't know if Dr. Atkins rounds or not. Did she mention that in her syllabus when she was going over it?
I don't remember.
Yeah. Okay. Well, it's nice to know, because 89.5 versus 90, that's a B versus an A. Okay. Let's see. And then if you go to the very end, there's something about me. Let's see, where is it? And this is a little background on me. Basically, I'm a local person. I went to Foothill High School here in Sacramento back in 1964 when they first opened it. Anyway, here's kind of my background. Okay, so anyway, that's where the syllabus is located in modules. And there's also a lecture and lab schedule there as well. And anything administrative will be located there. Are there any questions about where to find that stuff for all of you new people? Okay, so let's jump back into. Okay, so this is some typical dimensional analysis problems. This worksheet happens to be from Chem 300, which is basically what I'm supposed to be reviewing these today and next week. Okay, so these problems are asking you for density. Now, the definition of density is mass over volume. In the standard international units, we're talking about kilograms per cubic centimeter. In chemistry, usually we don't use kilograms, we use grams. So typically in chemistry, we're looking at grams per cubic centimeter. And a cubic centimeter is the same as a milliliter. So it's grams per milliliter. Now the abbreviation for liter is uppercase L. Milli is lowercase m. So it's little m, big L. Okay, so that is density, grams per milliliter. Now, the nice thing about knowing the density of something, you can use that as a determination of purity. For example, during the gold rush, they found two things that look like gold. One is real gold and one is not gold. One is called iron pyrite, which is a iron substance, but it looks just like gold. It's shiny and it's gold color, but it's worth nothing. Gold is worth a lot of money. So when these prospectors during the gold rush, up in the mountains here, they would bring their shiny yellow stuff to get paid. And the first thing they would do is they would check the density. And if the density wasn't the density of gold, then it wasn't gold. Hence, they weren't given anything for it. So this density is very historic in terms of our local California gold rush days. It's very crucial to determine whether you have pure gold or iron pyrite, which is known as fool's gold, because it looks so much. Now, if you look at fool's gold and real gold, the yellow is different and the sheen is different. But anyway, in those days, it was bright, shiny, and yellow. Oh my gosh, it must be gold. Okay, so density is a nice way to determine the purity of something. A lab I used to do in prior schools is we looked at old pennies and new pennies. Old pennies were, let's say 100%, they weren't 100% copper. And the new pennies were something else. They had a little bit of copper in them, and when we checked the density of the old pennies versus the new pennies, they were not the same. Because the new pennies had a combination of zinc and copper in them. Now, if you look at the density of copper and zinc, it's not the same as pure copper. Hence, we know the new pennies are not the same as the old pennies because the density was not the same. To determine density, you need two measurements. You need a mass and you need a volume. And then what happens is you divide the volume into the mass because you want grams per 1 milliliter. Okay. So it says, let's look at problem 60 here. Okay. Silver ingot has a mass of blah, blah, blah grams and a volume of so many cubic centimeters or milliliters. Excuse me. What's the density of the ingot? Well, we have the mass in grams. We have the volume in milliliters. So that's 34 grams over 8.5 milliliters. Okay. Divide the volume into the mass, gives us grams per 1 milliliter. So we're looking at how many sig figs is this answer going to have?
Two.
Two, exactly. Okay, so that answer is going to be 8.3. Okay, my calculator gives me 827, 529. Okay, so we go to the third place. That's 5 or more, so we kick up the second place from 2 to 3, so that's 8.3 grams per 1 milliliter. Okay, so that's silver. Okay, if we look up silver density, we can easily find that if we go to the net.
Professor Ferguson, how do we know that the sig figs was 2 again?
Down here. And whenever you multiply or divide, you look at the total sig figs for each thing you're dividing or multiplying. And your answer is going to be the lesser. Okay, so this is 2 sig figs. Oops. This has 4 sig figs. That means our answer has 2 sig figs. Does that make sense where the 2 sig figs come from?
Yes, thanks.
Okay, cool. All right. Now that determination you have to do each time you do a problem. Throughout the rest of the semester, Dr. Atkins, every chemistry professor in this department, physics professors, engineering professors will use sig figs in the class. Anything mathy will be using sig figs. Okay, so let's jump over to no, that's not what I want. Let's see. If we look up the density of silver, it's 10.49 grams per milliliter. So where's our ingot of silver pure? Now, if you've ever watched Pawn Stars or any of those others where they get an ingot and the first thing they do is they drill it, look to the core, because they could be putting iron in the middle of the core, they could be putting lead in the middle of the core to change the density. So what they do is they drill a hole totally into the ingot, past the middle, then they analyze it with nitric acid, and nitric acid will concentrated nitric acid will react with the silver in a certain way and give it a certain color if it's pure silver. Also, they'll look at the quality of the metal coming off the drill. Is it the same all the way through? So in this case, the silver has been changed with some lighter material because it's not 10.49, it's 8.3. Does that make sense? And this is very similar if we had gold. Same thing. And density of gold is 19.3. Notice that gold is a lot heavier than silver because the density is greater than the density of silver. It's almost twice as heavy as silver. So if you had a ring made out of pure gold and a ring made out of pure silver, the ring made out of gold is going to almost be twice the mass of the silver ring. Okay, so does that problem make sense? Number one, how to calculate density. Okay, we need a mass, we have a volume. We divide the volume into the mass so that it's to get it to 1 milliliter. Okay, that density then is almost unique for every single component, whether it's a pure component or a mixture. Okay, that includes gas. For example, carbon dioxide is a higher density than nitrogen gas. So if we have carbon dioxide in the air, it'll settle down to the bottom of the room you're in because its density is higher than nitrogen. So density doesn't matter whether it's gas, liquid, or solid. It's mass over volume.
So in this case, is the ingot not pure?
Yes, because it's not 10.49.
Density is different.
Yeah, exactly.
Okay.
So if you brought this into Pawn Stars, big old agate, shiny silver, and said, I want to get cash for it, this is what they would do. They would, one, drill it, and they would take the filings from the drill, assuming they're all consistent, and then calculate a density and compare that to pure silver. And what they would probably do is prorate your agate. In other words, not give you the value of a pure silver, but it's got silver in it. So they would give you the value, some downgraded value. But yeah, this is exactly how they do it. This is exactly analogously how the gold prospectors went in to cash in their gold. They did this same analysis. What is the density of the material you're wanting me to give you cash for? If it's gold, gold is that. Iron pyrite, in fact, let's look up the density of iron pyrite here real fast. Okay, so fool's gold is 5 grams per milliliter. Five. Versus 19. So you can see there's a big difference. So gold is going to be 4 times approximately heavier than fool's gold for the same volume. Does that make sense in terms of how they would determine the purity of gold during the gold rush days in the mountains here? Okay, so let's do one more density problem here. Let's see. Well, since we know the pure, we'll have to look it up. Let's do this one here. Are there any questions about that last silver problem? Okay. All right, let's just do one real quick here. Okay, so we've got a volume. Remember, density now is grams over milliliters. And remember, this is milliliters or cubic centimeters. In the case of solids, they usually go with cubic centimeters. In the case of liquids or gas, they go with milliliters. But it's interconvertible. Okay. All right. So we have 3 things here. We have the density, grams, milliliters. Now to calculate any one of the 3, we have to have the other 2. Well, we do know that the density of gold is 19.3 grams per, let's just use cubic centimeters since it's given like that. And that's equal to grams at 121 volume, cubic centimeter volume. So we can now solve for grams. So grams is going to be equal to okay. Notice the setup here, the centimeters cancel. What does it give us left over is grams. We're trying to calculate grams. So the given, in this case, the given is going to be 121 and 19.3. So our answer is going to be, how many sig figs is our answer? Yeah. How many sig figs is our answer going to be?
3.
Exactly. 3 sig figs 3 sig figs. The answer is going to be 3 sig figs. I abbreviate sig figs as SF. Most professors do. I'm not sure what Dr. Atkins does. Okay, so 121 times 19.3 is 2335.3. And that is 3 sig, is not 3 sig figs. We go to the 4th place. That's a 5. That means that kicks that 3 up to a 4. So it's 2340 grams. Now, some of you might put 234 grams. What's wrong with that?
The answer is like way off.
That's right. It's got to be sort of close. If it's not sort of close, then there's something going on. It doesn't make sense. That's the purpose of the 0 as a placeholder. Keep that value approximately the same. Because you've got 3 sig figs, 3 sig figs, but those are very different numbers. And this one is closer to that than the 234.
You can also annotate it, right? In scientific notation, that'd be the same thing.
Yep, exactly. Scientific notation is your friend regarding sig figs. Yes, exactly. Sig figs will always get resolved in scientific notation. Because you're forced in scientific notation to put the decimal number in the right number of sig figs. So whatever that is. So this in sig figs would be 3 sig figs times 3. Okay, so do those make sense? Okay, so what we're going to do now is I'm going to move over to another type of dimensional analysis. I'm going to continue to do dimensional analysis, but we're going to be using more chemistry stuff. Excuse me again. I'm so frustrating to have this cough, and I make my living talking. Okay, so this little unit I'm calling mole conversions. And coming into this class, it's starting to sound like me. Coming into this class, your background should have been that you've heard of the term mole before, but let's go over what it is. Okay, all industries have units that are associated with it. For example, if you raise chickens, you know about dozen, because normally you sell eggs in terms of 12 to the dozen, or if you make donuts, have a dozen donuts, okay? So the unit dozen, gotta have a lozenge here. So the unit dozen is used frequently in the baking industry in terms of donuts and in the chicken business in terms of eggs because it's convenient, okay? Convenient. If you're in the paper industry, a ream of paper is 500. Why a ream? Because 500 is a convenient unit to sell paper by. So when you go down to buy your copy paper for your printer, it's usually sold by the ream. And what they do marketing wise, they give you less so that it appears like the price is less, but the official unit of paper is a ream. Now in chemistry, and again, it's convenient. So what's convenient for chemistry? Because molecules are so, atoms and molecules are so incredibly small, we use a convenient unit as well, and that's 602 times 10 to the 23rd. That tells you how small atoms and molecules are. That 6 with 23 zeros after it is convenient. The mole is, in physics and chemistry, the most universal unit, period. Nothing will come even close to that. So everything is blah, blah, blah per mole, blah, blah, blah per mole, whatever. Whether it's electrons in a battery per mole being transferred from the cathode to the anode or vice versa, depending whether you're charging or discharging a battery. If it's the amount of water going through a system, whatever, it's so much per mole. So that's the underlying unit in chemistry and physics is the mole, and a lot of engineering as well, like chemical engineering, for example, and excuse me, a lot of other in geology, mole is used as well because geology is very, very chemistry focused. Okay, so we have one conversion factor then, which means we have excuse me again. So we have I'm going to say atoms, but it just as easily could be molecules. It could also be students. It could also be ducks. It's just a unit. Just like a dozen could be eggs or donuts. It's the 12 that's important here. In this case, it's the 602 times 10 to the 23rd is the important part. That's why it could be applied to atoms or molecules or whatever you're counting. Okay. And there's abbreviation for mole, it's MOL, which is not much of an abbreviation. Okay, so that's one conversion factor. Remember, with the conversion factors, you always have the inverse. That means it's going to be 1 mole. Okay, so remember, all conversion factors have 2 forms. And you need to use the right one so your units cancel. Okay. If we have a 6.02 times 10 to the 23rd atoms of, let's say, oxygen, and if we put them on a scale and weight it, we are going to get, oops. For oxygen. If we weighed hydrogen, we would get 1.01 grams, and this would be a mole of oxygen atoms and a mole of hydrogen. That would mean this is going to be okay, 602 times 10 to the 23rd atoms of oxygen, 602 times 10 to the 23rd atoms of hydrogen. Notice they're not the same. Just like we weighed 12 grapes versus 12 apples. Gee, they're not the same. Why? Why aren't 12 grapes weigh the same as 12 apples?
Their density is different.
Yeah, their density, their size, everything. You know, an apple's the size of your fist. A grape is the size of your, thumbnail. Okay. So if we took a dozen oxygen atoms and a dozen hydrogen atoms, they're also not going to weigh the same. Why? Because oxygen is not the same as hydrogen. Oxygen weighs more per atom than hydrogen because it's got more stuff in it. It's got more neutrons, protons, and electrons in it. So every atom is going to be different in terms of grams per mole. Okay, and we call that molar mass. In the case of a single atom, we're talking about atomic mass. Okay, the units of molar mass and atomic mass are grams per 1 mole. This information is all found on the periodic table. It is the decimal number in the periodic table. So I need to go pick up a periodic table here really fast and to I'm looking for a periodic table. Sorry, I should have picked that up before. Excuse me while I find a periodic table. Look what we have here, periodic table. Okay. All right. So here is oxygen, and notice the decimal number for oxygen, 16.00. That is grams per mole. Carbon, 1201 grams per mole if we have a mole of carbon atoms. Here is our oxygen. Now, periodic table, these will be in different levels of precision based on what periodic table is. The periodic tables frequently are rounded to 2 decimal places. For example, this one is. It depends on your class, depends on the lab, whether you're given, like this is 1.0007, blah, 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 blah. It just depends. This particular periodic table is 2 decimal places rounded to. Okay, so the molar mass, the atomic mass can be found from the periodic table. So let's look as an example. Water. Okay, this says we have 2 hydrogens, 1 oxygen. Hydrogen is 101 apiece. Oxygen is 16. So the molar mass for water, notice I didn't say atomic mass because it's a molecule. The molar mass for water is 18.02 because I added up 2 hydrogens, 1 oxygen gives us 18.02 grams per mole. Now, was that clear how I find the molar mass for a compound? Now, if you took Chem 300, you would have gotten this out the yin-yang. If you've had this in high school, for example, I taught a lot of high school. If you had me for chemistry in high school, you would have gotten this really early in the year. But if you haven't had any chemistry for a while, hopefully this review helps. Okay, So does that make sense? Does anyone question where we get these numbers from, the molar mass or atomic mass? Okay. So now we have some more conversion factors here. Oops. We have grams per mole. We have moles per gram. And this is specific to compound. So oxygen gas, O2, is different than water, H2O. Still conversion factor, grams to moles, moles to grams. This is not specific, because it's just a counting number. So O2 is 602 times 10 to the 23rd per mole. H2O is 602 times 10 to the 23rd. Nitrogen gas, N2, 602 times 10 to the 23rd. Anything is 602, okay? Anything. Molar mass, it's very, very, very specific because it's based on what's in the compound. Okay, any questions so far? I'm going to do some problems here in a second. Okay, so let's jump and do some problems here. Typical problems. Okay, how many grams are in 2.3 moles of water? Okay, number one, is there a chemical reaction going on? No, so we took that. Number two, what's given? .3 moles of water. What are we trying to calculate? Grams of water. Notice I put the compounds above what we're starting with. Now this is going to come into play, importantly, if we have a chemical reaction. What we're talking about chemical-wise is really important. So any kind of chemical type problem, whether it's a mole conversion, a stoichiometry problem, or whatever, always associate the chemical with the unit. Okay. So we have 2.3 moles. Two sig things. All right, do we have a conversion factor that has moles and grams in it? Yes, we do. It's called the molar mass. Okay, so the molar mass is grams per mole or moles per gram. Which we're going to use? Grams over moles or moles over grams? Which do you think we're going to use?
Grams per mole.
Yeah.
Yeah, grams per mole, exactly. Because we want moles to cancel. And how many grams are in 1 mole of water? We just did that. It's 18.02 grams per mole. No, that's a one-stepper because we're already at grams now. What are we trying to calculate? Grams. Now, how many sig figs is our answer going to have? Well, this has got 4. So how many sig figs is our answer going to have?
Two.
Yeah, 2. Because 2 is less than 4. So we're looking at, okay, so we go to third place. That's 0 to 4, so we just drop it. So our answer is 41 grams of water. That makes sense? Okay, so again, set up 90%, answer 10%. Now our answer is going to have 3 things in it. It's going to have our number. It's going to have our grams, our unit, and it's going to have sig figs. So our answer always has 3 parts. And normally I want to see the chemical. Dr. Atkins may require something slightly different or the same thing, but I always like to see the chemical that we're talking about here. So these would be the parts of an answer to get 10%. Okay, the actual number itself, which is a number crunchy from your calculator. What are the units? And the sig figs of that. Okay, so let's do another problem. Let's do one a little trickier. Are there any questions about this? Okay, how many molecules are in 456 grams of water? Okay, what's given? Oh, there's no chemical reactions. We can skip that one. So what's given? Look to the number to determine what's
4.26 grams of water.
Yeah, exactly. So the number is here, so that's our given. Now, sometimes we have 2 givens, and that's going to complicate things a lot, but we'll get to that later. Okay, so we have 4.56 grams of water. Okay, and what are we trying to calculate?
The amount of molecules
Yeah.
in that amount.
How many molecules of water? Okay. So do we have a conversion factor to go from grams to molecules? No. We've got moles to molecules and grams to moles. But no one, that means it's going to be a multi-step problem. And moles is what links those 2 together. So we're going to intermediate calculation to number of moles. So we need to have the grams cancel. And water we've already looked up for the molar mass is 1802. That gives us moles. And we need to go from moles to number of molecules. That is 602. That's the 23rd molecules per mole. Okay, so we're trying to calculate molecules, number of molecules. So based on our unit analysis, our unit cancellation, our setup leaves us with molecules. 90%. 90% for that. Move on to the next question. Now, during a test, I recommend that you do the setups first. In case you run out of time, you'll have the setups done, which are worth most of the points in the problem. Now, I'm going to be proctoring your tests. you're going to be given written tests during lab. If you look at the lab schedule, you'll see when those tests are going to be given. And my recommendation is to do the setups first. That'll give you 90%, assuming you do them right, that'll give you 90% of the point value of that problem. So if this problem is worth 10 points, that means this is worth 9 points. Move on. At the end, when you have time, then go back and work the problems for that 10%. That would be my suggestion as a strategy on taking your test. Also, start by going through really quickly and saying what's given, what are you trying to calculate? What's given, what are you trying to calculate? Every single problem. What's given, what are you trying to calculate? Then you look. Excuse me. Then how do you do the setup to get there? Okay, so let's see here. Let me crank this out. Now notice this problem is a little different than what you've been used to. Notice there's no, and normally in the bottom we have all ones. This time we have 1802. So this is the way I recommend doing this problem as far as your calculator goes. In your calculator, you're going to put $456 times 1, we don't have to worry about that, times 602 EE 23. Now anything on the bottom we have to divide key. Okay, that means you're going to have to divide key 1802. Enter. The ones we don't have to worry about. Now, if we had two things on the bottom that were not one, we'd have to divide key for each item on the bottom. I'm going to get to those in a minute here. Okay. All right. So we have 456 times 602 EE 23 divided by 1802. Okay, so we're looking at okay, so we have 3 sig figs, 4 sig figs, 3 sig figs. So our answer is going to have 3 sig figs. It means we go to the 4th place. That's 0 to 4, so we just drop it. So 1 point, and this is 10 to the 23rd. So our answer is going to be 1.52 times 10 to the 23rd molecules of water. So we have the 3 parts. We have the 3 sig figs, we have the numerical answer, and we have the units. That problem makes sense? Let's do another one. How many atoms of hydrogen are in 23.6 grams of water? Okay. All right, there's no chemical reaction. Our given is 23.6 grams of water. And we're trying to calculate the number of atoms of hydrogen. atoms, not molecules of water, atoms of hydrogen. Okay, so the first step is to convert to our intermediate moles. We already, know, I always use water because we have to look it up each time. So that's 1802. Okay, so that gives us moles. Now we're going to go to molecules of water. Notice I said molecules of water. So the 1802 is for the molecule of water, not hydrogen by itself, but the molecule of water. Okay. Notice I'm saying molecules now because the 1802 refers to molecules. The grams refer to molecules. Everything is molecule, molecule, molecule. But I'm talking about atoms now. So I've got to convert molecules to atoms. So as an aside here, let's talk about that. If I have 5 bikes, how many wheels do I have? Right,
10 wheels.
How many?
10 wheels.
Yeah. Well, how'd you get 10?
I multiplied each bike by 2 wheels.
Yeah, because there's 2 wheels for each bike. Okay. If I have 100 bikes, I'm going to have 200 wheels because for each bike we got 2. So the conversion factor for bike to wheels is 2 wheels per 1 bike. Conversion factor. So we need a conversion factor for water in atoms to molecules. Okay, so if I have If I have 5 molecules of water, how many hydrogens do I have?
Ten.
10, yeah, because each one's got 2. If I take the water apart, I've got 2 atoms. So for each molecule of water, I have 2 atoms, hydrogen. That's our conversion factor. We needed one more step here to get us from molecules to atoms. And that's a real important step. Now, sometimes it's 1 to 1. Like if I said, how many atoms of oxygen are in 23.6 grams of water? This would be 1 atom per 1 molecule. So you're saying, why even put it in? Because the units won't work out if we don't put that in. Remember, the units have got to all cancel. If they don't all cancel, then it's not going to work. Dimensional analysis requires unit cancellation. Okay. Is everyone okay with the setup?
I have a quick question.
Hmm?
I'm a little confused on when we use like the formula mole over grams, and just And like how it could be used opposite gram over moles. Like how do you know which one to use? If that makes sense.
Yeah. Remember the conversion factors, you always have two of them, like you said. We have mole over gram or gram over mole. Notice that the units have got to cancel. So the first thing here, we got to get rid of that gram. So the way to get rid of a gram is to have it on the bottom on the next unit over. Hence they cancel. We have moles here. We want to get rid of it so it's on the bottom here. Does that make sense? Because you always have a choice. Because there's grams over moles, moles over grams. Was that your question?
Yeah, that makes sense. Thank you.
Okay. So always remember that. What we start with, we got to cancel it. Because we don't want what we start with given. We want to start with what we want to calculate. That's why we always have to cancel it. So that means that grams, if you start with grams, has to be on the bottom of our conversion factor. If we started with, in a minute here, I'm going to give a problem on so many molecules. How many grams is that? So then the molecules are going to have to cancel. Okay, and I just worked out the answer, and it's 1, 5, 7, 6, blah, blah, blah.
I have a question about the setup too.
Yeah.
Instead of doing 2 atoms on top and 1 molecule on the bottom, could you do 2 moles of hydrogen on the top and then 1 moles of water on the bottom?
I'm not sure. You're talking about which part again?
It's going to be the last part, but then you would do it before Avogadro's number.
Oh, right here, right?
Yeah, but then you would put that before Avogadro's number and put 2 moles hydrogen on top and then 1 mole water on the bottom.
Yes.
Okay, perfect.
Yeah. Yeah, because your units would then cancel. Most of the time, that would work. And if you're taking a test in my class and you put that down, it'd be fun. I would probably, I make a note, I don't know if I would or not. Normally, excuse me, you guys. Oh, sound like a tuberculosis ward here. Normally, it's all done in a molecular level, all the calculations. Then at the end, we tweak it for atoms, normally. Because everything is given at the molecular level. You know, the molar mass is molecular, the given is molecular, you know, everything's molecular. And at the end, we're talking about, and you can also say, by the way, this would be, the alternate way to write this would be 2 moles atoms per 1 mole of molecule. Write it that way too. I think that's more confusing than just 2 atoms per 1 molecule, but that would work too, because the moles would cancel and the molecules would cancel. So, okay, so are you okay with that answer?
Yeah, thank you.
Okay. All right, I think that question means you understand the process. Because your units would all cancel out and give you the same answer, unit-wise and everything. So
yeah, I was just familiar with the other way, like using it from the actual like formula, then doing like atoms for molecules.
Okay, yeah, and if that's the way you were taught, continue doing it that way. Okay.
Okay, thank you.
The only problem is, I'm not sure what Dr. Adkins would say in this instance. If you were in my class, I would tell you continue doing it that way. Because to unlearn something and learn something, it takes time to unlearn something, and then takes time to learn something.
Yeah, she did this way in her lecture video too. So I just want to make sure it would be okay for lab too.
She did it the way I showed it here?
No, the 2 moles hydrogen over 1 mole water.
Oh, okay, okay. Yeah, so that's fine. So you, in her lecture, she covered all this stuff?
She did it like how to use a conversion factor from a formula. That was her like last 2 lecture videos.
Okay, well, there should be, the purpose of the first 3 labs is kind of a dry lab, which is a review. So I'm reviewing all the stuff that you're going to have in the beginning of Chem 400. This stuff, and she's going to assume you're very familiar with this already. So she's going to go through this fairly fast. Okay, so let's do one more example. Then I want to get into something called stoichiometry.
Professor Ferguson?
Yeah.
I have a question. So why do we use 2 atoms instead of, like, why 2 atoms is my question.
Well, when we take the molecule H2O apart, we have 1 atom of oxygen, 2 atoms of hydrogen. And you could put hydrogen here also if you like, and then water down here. So then the waters would cancel.
Oh, so it's specifically because we're trying to find hydrogen only?
Correct. Exactly. Okay. Exactly. And it would be, if this was changed to oxygen, for example, this would be 1 atom. And 1 over 1, you'd say, well, why even bother? But the point is the units wouldn't cancel unless that was in there.
Okay.
So that is part of the setup.
Okay, thank you.
Okay, I'm going to go on to yet another problem that's, okay, so let's, oops. Okay, so let's do, okay, how many grams are in 3.45 times 10 to the 34th molecules of water? It's very similar to this previous problems. Okay, so we have, are there any chemical, is there a chemical reaction going on here? No, so skip that. What's given? Look for the number. Okay, 3.45 times 10 to the 34 molecules of water. We're trying to calculate grams over here. So again, set up. There's no direct. There's no direct. Oh, time for a little oxygen. Sorry, you guys. I am so sorry for this cough. Okay, so we've got to convert the number of molecules to the number of moles. That's going to be 602 times 10 to the 23rd. By the way, that there's a name for that number. It's Avogadro's number. Okay, so molecules cancel, gives us moles. Now we're going to go from moles to grams. It's got to cancel. And that for water, again, it's going to be 1802. Now everything's canceled except for grams. What are we trying to calculate? Grams. So this problem is a little different number-wise, but it's the same process. Given what are we trying to calculate? Set up every single time. Okay, so on my calculator gives me 103.27, blah, 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 which tends to be 12. Okay, so we have 3 sig figs, 3 sig figs, 4 sig figs, 3 sig figs as an answer. Okay, so we go to the 4th place. That's 0 to 4. So we drop it. So the answer is going to be 103 times 10, 12 grams. We've got sig figs, numeric answer, and units. So these problems all share the same deal. 4 steps. Chemical reaction, what's given, what are you trying to calculate, setups, every single time, no exceptions. Okay, are you guys okay with so far? Okay, I see lots of yeses and regarding roll call, I don't need to do roll call because Zoom automatically tells me who's logged in. So I just log into Zoom and I go to reports and it tells me participants for this session. So it's not a big deal at all. Okay. Now, more practice. Jordan, I agree. So to get more practice, where do you find more practice? Okay. You're going to bump over to our handy dandy Canvas class. Let me do one thing. I'm going to go to modules or files. Since we don't want to download them all, just go to files, lab review sheets. This is under mole conversions. And here's a whole bunch of worksheets on mole conversions. These liters are for gases at standard temperature and pressure. Okay. All gases are 22.4 liters per mole at standard temperature and pressure, STP. Now you're going to be learning a lot about gases at different standard temperatures and pressure, or excuse me, different temperature and pressures that are not standard. And that 22.4 only holds if it's at standard temperature and pressure. Pressure is 1 atmosphere, temperature is 23 degrees Celsius. Okay. So that's where your more practice are. Is under all these. Okay, so I've given you lots lots and lots of practice. The mole conversion worksheets zip file is if you want all the worksheets together, and that's under modules. Under mole conversion worksheets. In fact, let's move that up to here. And this up to here. And then this here. I'm putting these in the order I'm going to be covering them in the lab review. Okay, does that make sense where everything is located under Canvas? Okay. And yes, you will, Monet. You'll be counted because you're officially logged in to Zoom. Okay. All right, so let's pop back over to OneNote. Now we are going to cover, let's see, we've been talking, I have another probably 45 minutes more to talk. What I want to do is talk about stoichiometry. Okay, these are the 4 steps. Again, there's a reaction, balance the chemical reaction. What's given, what's calculated, and then there's a setup. Okay, when there's a chemical reaction, there's a little more to it, the calculations. Step number 1 is we have to balance the equation. So I want to go over balancing equations. So what is a balanced equation? That means that, that means the number of reactant atoms equals the number of product atoms. Not molecules, atoms. So if we have 5 atoms of oxygen, you're going to end up with 5 atoms of oxygen. Recombined, but there's still 5 atoms of oxygen. So we need, that means we are going to take an inventory of atoms. That's what balancing the equation is. We need to have that inventory of atoms balance. Okay, so let's look at a typical chemical equation. So let's take methane. Methane is CH4. And we're going to burn that in oxygen gas. Oops. Okay. Okay, so whenever we burn anything, that's called combustion. And combustion, most of the time involved involves oxygen as an oxidizer. Doesn't have to be though. So we have now you're going to get into the 6 types of reactions and a unit in Chem 400. And you should have covered that in Chem 300. But there's 6 types of reactions. One of them is oxidation reduction. And combustion is a form of oxidation reduction. That means electrons are transferred. Okay, so we have a fuel and an oxidizer. The fuel in this case is methane, the oxidizer is oxygen. Okay, so that's just a precursor of what's going to be coming when we talk about types of reactions. Okay, so when we burn methane and oxygen, where we have plenty of oxygen, excess oxygen, that's important, we're going to end up with carbon dioxide and water. Okay. Step number 1, is this balanced? We don't know. We have to check it first. Okay. To check an equation whether it's balanced or not, we have to take an inventory of the reactant molecules start with reactants, recombine the atoms in the reactants to produce product. So the products are recombined atoms of the reactants, but we have not destroyed anything. So if you have X amount of atoms of carbon, you have to end up with the same X amount of carbon atoms in the end. Otherwise, we have a big explosion. It's called a nuclear reaction. We're not doing that through non-nuclear reactions. Okay. All right, so we have to take an inventory. In the inventory, we have carbons, hydrogens, oxygens. We have 1 carbon on the left, 1 carbon on the right. How do I know that? There is a coefficient up front here. And I'm going to give myself more room. Now, this coefficient of 1, and we don't have to put the 1 down, it's totally optional. If you want to put the 1 down just to be complete, that's perfectly fine in my class. Okay, so we have 1 carbon. 1 carbon, okay? How many hydrogens? We have 4 hydrogens. 2 hydrogens. 2 oxygens. 3 oxygens. So our inventory is off. That means this is not a balanced equation because the inventory is off. Products, reactants, atoms, numbers don't match. Okay, so now we have to change the coefficients. These guys here. So they do match. That is the only number you can change. You cannot change the subscripts. If you change the subscripts, it's that molecule is no longer the original molecule. Okay, so let's clean this up here. So we can change the coefficients all we want. Okay, so 4 hydrogens on the left. If we change this to 2, that'll give us 4 hydrogens and 2 more oxygens. So that gives us 4 oxygens total. Okay, so carbons are good shape, hydrogens are good shape, oxygens are not. So we're going to change the coefficient for the oxygen to 2. So now we have a balanced equation. Why is it balanced? Because our inventory is balanced. Reactant atoms equals product atoms. For each one, in this case, we have 3 different atoms. Each one has to be balanced, not just one of them. Okay, so this is crucial to balance, to do a problem involving a chemical reaction. You have to, what is the reaction, number 1, and number 2, balance it. Okay, it's crucial because the calculations are going to involve the ratio of the coefficients. Okay, so okay, number 1, what does a balanced equation tell us? It tells us the molar, there's that mole again, ratio of the okay, so it tells the molar ratio of the reactants and products to one another. Okay, what do I mean by that? That means, for example, that two moles of oxygen gas reacts with 2 moles of water because the coefficients are 2 to 2 or 1 to 1 since they're equal. One mole of methane reacts with 2 moles of water. So if you have a mole of methane, you end up, after the reaction is over, you end up with 2 moles of water. These are going to be molar conversion factors in the form of a fraction when we get to do the stoichiometry problem. Okay, so that's one thing the balanced equation tells you. It also tells you the molecular ratio of the reactants and products to one another. Okay, so it's a molar and a molecular ratio. So I could say 2 molecules reacts with 2 molecules of water. one molecule of methane reacts with 2 molecules of water. So it's both a molar and a molecular ratio. Okay. It is not a mass ratio. It's not a mass ratio. It's molecular and molar only. Because we're talking about moles now. In moles, when we convert to mass, unless we're using the molar masses, it's going to be different because each compound has a different molar mass because it's made up of a different combination of atoms, each atom weighing something different. Okay, so let's do, and of course, if we go to good old Canvas, under modules, under stoichiometry, I have lots of equation balancing practice for you. In fact, I have lots of worksheets here. Look at them all. Lots of practice in this. Now, this is real important to get down solidly for this class. You'll be doing lots of stoichiometry in here. Lots of stoichiometry. Okay, I'm going to do a couple more examples of equation balancing. And I'm going to do one simple stoichiometry problem, and then we're going to get into it heavy duty next week in class or in lab. Okay, so let's see here. Are there any questions about balance? Has Dr. Atkins covered balancing equations in lecture yet?
No, she hasn't.
Okay. Well, good. Then this will be a good introduction for you. Okay. Okay. Let's take let's take a butane lighter. Butane is a 4-carbon hydrocarbon. It has 10 hydrogens. And let's burn that in an oxygen environment. Okay, so this is butane, and this is oxygen gas. Okay, and we are going to get, assuming we have excess oxygen, we're going to get carbon dioxide and good old water. Okay, so is this balanced as written? Well, we have to take inventory first to determine that. Okay, so we have carbon, hydrogen, and oxygen. And how many carbon we have left? We have 4, because this is a 1 now. Remember, you don't have to write a 1. So that's 4 carbons, and we have 1 carbon on the right. So immediately we have an issue. Move this up a little more. Okay, hydrogen 10 on the left, 2 on the right, 2 oxygen. Okay, so this thing is wacko unbalanced. Nothing is balanced, wacko, okay? So you can go down the list here and start with carbons, balance them, you start with hydrogens. What I suggest you do in a balanced equation environment is leave the simple ones to the end. Now, what I mean by simple is, let's look at butane here, C4H10 versus O2. O2 only has oxygen in it, so you can't get any simpler than that. The problem with butane, if we change the carbons, we change the hydrogen. We change the hydrogen, it changes the hydrogen. Over here, oxygen, if we change oxygen, because it's in multiple molecules, it's gonna complicate things. So we're gonna leave the O2 to last. Then you can either start with hydrogens or carbons. Let's just start with carbons, okay? So if we put a 4 here, that'll give us 4 carbons, but it's going to modify our oxygens. So we have 8 and 1 is 9. Okay, let's look at hydrogens. We have 10 here. If we put a 5 here, that'll give us 10 hydrogens, but again, it's going to modify our oxygens. So we have 8 and 5 is 13 oxygens. Okay, so what's left? The O2. The problem here is oxygens come in twos. We have an odd number here. So we're going to use a fractional coefficient just to balance the equation. I'll repeat that. We're going to use a fractional coefficient only to initially balance the equation. Then I'm going to fix the fraction afterwards. Okay, so what do we multiply 2 by to get 13? Well, if we multiply 13 over 2 times 2, we end up with 13. So our equation now is balanced. However, there's an issue. The issue is fractional coefficients. We have to get rid of the fraction. Does anyone know how to get rid of the fraction in front of the oxygen gas?
Multiply everything by 2.
Exactly. So if we multiply 13 over 2 by 2, it becomes 13. But this is like an equation. What we do to oxygen, we have to do to butane, we have to do carbon dioxide. So everything's multiplied by 2. Okay. So that means this becomes 2. This becomes 13. This becomes 8. This becomes 10. So I multiplied everything by 2. If we multiply everything by 2, the balance remains. That means we have 8 of these, 20 of these, 26 of these, 8, 20, 26. No fractions. Now you can do the fraction step. Now, I was hoping you'd cover this in the lecture with Dr. Atkins, because some people, to balance the equation, will put in a fraction coefficient like I do, and then we get rid of it afterwards. Some teachers say no fractions at all, and then they modify things. So anyway, this is a very consistent approach I just took with a lot of textbooks. You throw in a fraction just to balance it, then we fix the fraction afterwards, okay? So our balanced equation is That's the balanced equation. No fractions. So this 13/2 is just an intermediate fraction or equation, okay? So it's okay to use fractions just to get it balanced, then clear the fractions afterwards. And usually it's going to be 2. Sometimes it's 3, but most of the time, I would say 95% of the time, usually you're multiplying everything by 2. Okay, so I'm going to end this here. Now let me do one stoichiometry problem first. I'm going to show you where this whole point of balancing equation. Then we're going to get into stoichiometry big time next week. We're going to be doing simple stoichiometry and limited reactant stoichiometry, which is significantly more involved. Okay, so between now and next week, I want you to practice what we've gone over today, particularly balancing equations. If this is kind of confusing, I gave you a ton of practice. Mole conversions, I gave you a ton of practice there as well. Those are really important to get down by next week. I can't emphasize that enough because I'm going to assume you've done these worksheets for next week. Okay, so let me show you a simple stoichiometry problem. Okay, so stoichiometry problem again is going to have step 1 is balanced equation. Number 2, what's given, what's to be calculated on the right, and then there's the setup. Okay, so what are we looking at here? As a stoichiometry problem. I'm going to use this equation here. So as our example. Okay, so okay. Sorry. Don't I sound great? Okay. All right. So we're going to take methane and we're going to burn it in an oxygen atmosphere, giving us water and carbon dioxide. Okay. What if I burn 4.56 grams of methane? How much water do we make? How many grams of water? Okay. So step number 1, what's given? Well, that's what's given. But what's the first step? Chemical reaction. Balance it. Okay. So here's the chemical reaction, and we balanced it using our inventory method. Okay. That's step number 1. Step number 2 is what's given. Okay. Excuse me, not, okay. 456 grams of methane is given. What do we want to calculate? Grams of water. Okay. Now, we're not with the same molecule like we were previous. Okay. We've changed molecules. changed molecules in the calculation. We need a balanced equation to relate the methane and the water. Okay, from the balanced equation, this is a molar relationship. Grams won't work. Mass ratios do not work. We have to convert to moles first, okay? That means step number one is convert the 456 grams to moles, okay? Grams have got to cancel. So we have moles on top. So that's the molar mass of methane. Okay, carbon is 1201. And hydrogen is 101 apiece. So that's 404. So methane is 1605 grams per mole. It was 1605, right? Okay. All right. Now we have moles. Now we can apply the molar ratio from the balanced equation. Okay. So this is from the periodic table. This is from the balanced equation. Okay. And we need to have the methane cancel. So the methane is going to be on the bottom. And we're calculating water. So the water is going to be on the top. And what are the molar coefficients from the balanced equation for water and methane? Water is 2, methane is 1. This is why we balance the equation for this middle step. Now, what this gives us is moles of water, if we cancel everything out. We want grams of water. So now we have to go from a mole to gram ratio for water. Okay. Moles have got to cancel. And 1802 again for water. So everything's canceled except what? Grams of water. What are we trying to calculate? Grams of water. PT is periodic table. So we have two calculations based on molar masses. And then we have the balanced equation. So that's the setup. Are there any questions where I got those numbers? Okay, let's see, I'm looking at the chats here. Okay, so Dr. Atkins does go over it this week and she uses fractions. Good, we're consistent then. Good, good, good. Okay, does everyone know where all these numbers come from? Okay, so now we just need to grind this out. Again, this is 90% of the problem. This was worth 10 points. You're looking at 9 points right now in my class. I don't know how Dr. Atkins balances things out. She and I have worked together before. It's just that I forget sometimes when she does things. Okay, so we're looking at 456 times 2 times 1802. Hit the divide key, 1605. Okay, looking at 3 sig figs, 4 sig figs. How many sig figs is this? This is a trick question. Okay, when you balance the equation, it's a perfect ratio, not measured. So how many sig figs is this?
It's exact, so we can't. There's no sig figs, I guess.
Exactly.
Okay.
So that's infinite sig figs. So that doesn't come into play regarding determining our sig figs for our answer. Okay. All right. So our answer is going to be 3 sig figs. We go to the 4th place. We just drop it. That means because it's 3, so it's 10.2 grams water. So if we burn 456 grams of methane perfectly in excess oxygen, we end up with 3.2 grams. This is called the theoretical yield. Theoretical means, in reality, actual yield is going to probably be different. 99.999% of the time, it's lower. Okay, so theoretical yields is everything goes perfectly, and you know how life is. We get 10.2. Now, next week I'm going to talk about theoretical yields. Say we did this lab when we weighed the water and we end up with 9 grams. So we go 9 over 10.2, convert that to percent, and that would be the percent yield. Okay, so we're going to do lots of these problems next week, but I wanted to give you an idea of kind of where we're going with this. And this is called a gram-gram stoichiometry problem because we're starting with grams and ending with grams. We can have a molecule to gram stoichiometry problem. We can have a gaseous liter to gram. You know, there's all these combinations, but the simplest one is gram to gram because we're using molar masses. Okay, is there any questions about where I got these numbers? Again, every stoichiometry problem we have that has one given works this way. It's in 3 parts. Convert the given to moles. We do the mole ratio from the balanced equation. Then we convert back to what we're calculating it to. Every single problem. Okay, I'm going to end the lecture here, and we're going to pick this up next week in lab. Now on Thursday, I gave everyone the Zoom session for Thursday. You're more than welcome to join me on Thursday. I'm going to be covering the same exact material. But it doesn't, you know, for this week, it doesn't matter which session you choose. So you can do both or one of the two, okay? Next week, it's imperative you go to lab on Tuesday if you're in Tuesday lab, go to Thursday lab if you have Thursday lab. We have very little room because I've overbooked this class on purpose because frequently we have a couple of people drop, so the number comes down to what we should have. By state law, I cannot overbook the lab. So if 10 people show up on Thursday when they should have been on Tuesday, you can't do the lab. Lab points are easier points than test points, big time. So you want to maximize your lab points to go against your test points. Okay. All right.
Just to clarify,
Yeah,
is next week in person?
correct.
Okay, thank you.
Yes, well, all of you get to see me live with my lozenges. Because the problem is in lab, you're not supposed to eat or drink. I don't know what I'm going to do. I guess I'll just cough away.
So for next week in lab, we just bring the goggles and then like a lab book, right?
No, I want you to come like it's a wet lab. So I want you to bring a lab coat too.
Okay.
If you haven't, now, you can use anything that covers approximately the same as the lab coat. I had a student that was a butcher, and for his lab coat, he just brought in his butcher's apron, not apron, but his coat that he used to butcher stuff. And it had, stains on it and everything, but, it served the same purpose. So it doesn't have to be an official chemistry lab coat. I want you covered from your shoulders down to your, mid thighs, something like that.
I have a question. Will class still be held in the Lillard Hall 206?
You mean in the lab?
Yeah.
Yeah. Yeah. And unfortunately, lab lecture is not as fancy as lecture hall lecture. But no, we'll do fine. It also will not be 4 hours also, because I have to cover the lab contract, safety contract, the layout of the lab, as well as talking about stoichiometry problems next week. Okay, are there any other questions? Okay. A poncho. The only problem with I would say no. The problem with the poncho is if it's open in the front, it'll probably be okay. But if it's not open in the front, some ponchos are basically a big circle with a hole in it for your head and a hood. I would try to go for a lab coat. Yeah, I would probably get pushback on that from the department. So, okay. I haven't been there either in person. Yvonne, we're in the same boat.
Yvonne, I went before, like during summer, and there's like one parking building because I asked a security guard. It's all the way like in the corner, and then the Lillard Hall is the last building all the way towards the right of the parking structure.
So it's close?
It's the farthest building from the parking structure, basically.
Oh no.
Like the on-campus parking structure. Yeah. The issue was I couldn't go inside because it had spikes up. So I don't know if we need like a parking pass or something.
Oh shoot.
Yeah. So I don't know where we would park if the spikes are still up.
Okay. Thank you.
My daughter went to Sac City. I went to American River back in 1969. My daughter went to Sac City, I guess in the 90s. Yeah, trying to think back. She's in her 40s now. Then transferred over to Sac State. I think parking is still free. Does anyone know?
From the last announcement from fall semester, they said that spring and fall 2020 and 2021 and 2022 were going to be free. Okay. I can also double check with, I work for the Raza Center, and I can.
Okay, could you check and then send a note to the class?
Parking is free because for athletes and stuff like that who have been on campus like every day, we don't have to ever pay.
Oh, thank you so much.
You guys have enough to pay. Students, what bugs me about publishers, students have the least amount of money, period. And when you buy a textbook, what they charge is, always close to $200, sometimes more. For anatomy, physiology, for example, it's usually close to $300. And students, unless you have some kind of a grant or something like that, or your parents are paying, but if you're on your own working for it, that's why I like to use public textbooks. They're called OER. And Davis publishes one. There's a number of them out there that are pretty good. Okay. All right. Well, I will see you all then next week. at 7:30 in the morning. And you're more than welcome to join my Thursday Zoom session. I sent everyone the Zoom URL. So anyway, everyone take care, and we will see you later. Get to meet everyone in person. I'll be wearing my tie-dyed lab coat, by the way. That picture you have on Canvas is me in my tie-dyed lab coat. All right, everyone, take care.
Professor, I have a question.
Yeah.
But it's unrelated to lecture today. It's just more so like about the class itself. So I'm curious on the week of February 7th, it says that we'll have experiment 1 basic lab techniques due, but I'm just curious, what does that involve exactly?
Buy the lab packet and they'll show you the lab.
Okay.
All the labs are in that packet. Has anyone bought it? What is the cost?
I haven't been able to buy it, but I'm assuming the information will be like on the syllabus somewhere.
Yeah, well, it's a bookstore, and you go there, and it's all departmental labs. So it's just a cost of printing plus I think about 10% of average to cover overhead.
Oh, okay.
It's pretty inexpensive. When I used to teach the prereq for nursing, the organic and biochemistry, and the lab manual was $90. And on top of their textbook, so you're looking at $300, and it's like, so anyway, departmental labs are cheap, and that's what we've done. We've also used the free OER textbook as well to minimize cost for you guys.
Okay. And so is there a quiz next week when we show up?
No, you're going to have a safety quiz. You're going to be asked to watch the American Chemical Society's safety video, and then there's going to be a quiz based on that. And I think I need to talk to Dr. Atkins whether I'm to be making it up or I'm going to use hers.
Okay.
But it's not very hard. It's like.
I see. I think the quiz may be for the lecture and discussion rather than lab.
Yeah. Yeah. So it shouldn't be too bad. Okay. And Miriam gave me a link in chat to parking. So make sure you pick up that lab manual before, you don't really need it next week, but you will need it the week after.
Okay.
Also, closed-toed shoes. So next week, we're doing a dry lab like we're doing a wet lab. So you're going to be wearing goggles. You and I both will be wearing goggles. We all will be wearing lab coats, and we all be wearing closed-toed shoes.
So just